Hi, welcome to another lecture on precalculus. Today's topic is angular and linear speed. Well, I've written two abbreviations here. You must have heard about them, RPM and MPH. Of course, the first one is rounds per minute, and the second one is miles per hour. So this is these are two indications of speed, and round per minute is related to rotational speed, and miles per hour is for linear speed. Oftentimes these two are related to each other, and we are going to look at problems in this regard. So we are going to look at a Ferris wheel, a bicycle, planet, and the ceiling fan. So the idea is these are things that turn. So we can measure the speed by either talking about angular speed, how fast they turn, and then the other one is by checking to see the linear speed. For example, if you're looking at a fan, you might care about how fast it turns. You might care about how fast something at the tip of the blade is going around. If you're dealing with a Ferris wheel, one concept of speed is that how fast it turns, and the other one is, well, on the edge as you go around, what is your speed? If like you are on a road, you measure your speed as miles per hour or some other indication of speed, what would that be? Same way with all the other examples we had before. So here we always have a circle, and on this circle some point on the edge is marked, and we are checking to see how fast this turns. So that's going to be rotational speed. We can also check to see, well, if this was a road and this object was going around on this road, what would be its linear speed? You remember we had a connection between three quantities. If you have a radius of this circle, and then you have this angle, say theta, and the length of the arc in front of it, the arc length, if it is sometimes shown by L or sometimes shown by S, these three quantities were related to each other. What's the relationship? S or L is the radius times the angle. In this case, angle is measured in radians. In fact, this is the definition of radius. That is, you can think about the angle itself is the arc length, let's say arc length S, divided by the radius R. So this is the arc length, and this is a radius length. You notice numerator and denominator, both of them are measurements of length. Therefore, when you divide it, the angle theta that you get is a dimensionless quantity. It doesn't have any dimensions. If you multiply that dimensionless quantity by r, so r times theta, out comes another object in units of length. When we talk about theta measured in this style, we refer to it as having the unit of radians. Radians, even though we refer to it as radians, it is a dimensionless quantity. So what are the typical questions that we have here? A Ferris wheel at a carnival has a radius of 36 feet. Suppose it turns at the rate of 90 revolutions per hour, and we want to find out what is the angular speed and what's the linear speed. Well, how do we measure the angular speed? Let's go back here and let me rewrite this formula. S is equal to L times, S is equal to R times theta. So this is the distance. If I take the distance and divide it by time, I get the speed. So S is the distance traveled divided by time will be the speed. That's how fast we are going around, measured in, say, miles per hour, feet per second, or whatever it is. On the right hand side, the radius is a fixture. It is not changing. But the angle that we are turning, this angle, as time passes by, we are going to bigger and bigger angles. So if I take that angle and divide it by time as well, I get the angular speed. So what we have here is, this is called the linear speed, and this one is called the angular speed. Linear speed is familiar to you from the courses you had before. A typical notation for that is V, V for velocity. Okay, so V for velocity, R is our radius. For angular speed, we are going to borrow a Greek letter omega. So omega is written like that. So V is equal to R times omega. That is an important formula in this section. So linear speed is equal to angular speed times radius. In many of these discussion here, we have a way of referring to making a complete rotation, and so a rotation, it comes up in all of these problems. Sometimes it's called revolution, so it is another word for it, revolution. One revolution means going around once, or one round, that would be another one that starts with R again. Sometimes we call it a cycle, sometimes maybe we call it one spin, sometimes we call it a turn. Quite a few words in this, so, like if you are on a racetrack, and say racetrack is in the shape of a circle, you are going through laps and so on. Even sometimes we might talk about an orbit, because like in a planet going around the sun, turning around itself, it might go through one orbit. All of these, one of any of these things is equal to, so if you go around the circle once, how many radians is that? It's equal to one rotation is equal to, is equal to how many radians we said? It's equal to 2 pi radians. Okay, so we need to remember that. So let me abbreviate this thing by saying, so let's say use this word, one revolution is equal to 2 pi radians. Let's go ahead, take a look at some of these problems, see how we are going to attack it. So here we have a Ferris wheel at the carnival, has a radius of 36 feet. So it is a big Ferris wheel. It has a radius of 36 feet. It is turning at a rate of 90 revolutions per minute. So this is going around at 90 revolutions per minute. Now, when we want to make use of this formula, we have to remember this theta here is not revolution, it's a radians. It's a radians. So in any of these problems, if you want to do a conversion, we have to remember going around the circle once means consuming 2 pi radians. So here 90 revolutions per minute, I will have, oh excuse me, I made another mistake. This is, let me correct myself. This was per hour, so I have to make a correction this year. I guess I wasn't thinking 90 revolution per minute. All the passengers on that Ferris wheel will be dead by now, so it's good that we didn't make it go around that fast. 90 revolution per hour. That's more reasonable, and it's not going to make us throw up or anything. So first object we are after is what is the angular speed, and here is the unit that we are after, radians per hour. So angular speed, we write it omega. Remember again, we said one revolution is 2 pi radians, so 90 revolution is going to be 90, so it's 90 revolutions per hour. We multiply it by 2 pi radians per revolution, and out comes 90 times 2 pi, and the final thing is radians per hour. So simplify it now, 180 pi radians per hour, and that's what it's asking us, radians per hour. Well, it is saying to round it, so again you use your calculator and then you round it at the end. It always says do not do any intermediate rounding, just so that there wouldn't be any fight over some digits lost here and there. Okay, next one, more interesting. What's the linear speed of a passenger? Now it's asking for feet per minute. So somebody is here, so you are here with your friend or something, and you're going around just like being on the road. You want to know what is your speed. So we say to convert from angular speed to linear speed, all that we have to do is to multiply by the radius. So we say v is equal to r times omega. Now it's simple enough to just multiply. The major issue here is to get used to unit conversion. Okay, so unit conversion, let's write it carefully. So we have here, we are told that our Ferris wheel is 36 feet in radius. It's 36. So I have to multiply. This is 36 feet, and then I multiply 180 pi radians. This is per hour. Next, I look at the unit that is required from me. The unit is feet per minute. So thankfully this is already in feet. I don't need to worry about that. All I have to do is that instead of hour, I want to have in terms of minutes. So how do I do that? I make a fraction. The unit I want to get rid of, I put that opposite of this thing. So if this is in the denominator, this one is going to be in the numerator, and vice versa. And I write the equivalent of this in the unit I want, which is now in minutes, 60 minutes. Or just reason it out that this is the speed in feet per hour. If I want to figure out per minute, I'm traveling much less, so I should divide by 60. So just either notice that you cancel these things and get what you want, or just reason it out if you have to divide or you have to multiply by 60. So out comes 36 feet that we had, then 180 pi, and then divided by 60, and this is going to be at the end in terms of Now we don't write the radians anymore because we said it's a dimensionless. It's just going to be feet per minute, so it's going to be feet per minute. Why didn't I write the radian again here? I'll explain at the end. At the beginning we said radian is it's a dimensionless quantity. When you multiply it by a unit of length, you just get the same unit of length again. Okay, this is what you get here. In this case, of course, you can go simplify and make it a little bit cleaner, because these things simplify here, becomes 3 times that becomes 108 pi. But it is asking us to do an approximation at any rate, so you want to use the calculator. But it's always good practice to simplify things by hand, to just get used to this type of simplification. So that was one example. Here's another one. It is a bicycle. There's a bit of a difference between a bicycle and a Ferris wheel. What's the difference? A bicycle is, well, the whole bicycle is moving. And the Ferris wheel, well, you certainly hope the Ferris wheel is not moving. That's gonna be fine. So when the object, when the whole wheel is moving, we actually have a rather interesting and rather complicated thing that you're going to study in your physics or your calculus classes. Let me just take a moment to show you how interesting it is. But as far as the problems in this section is concerned, that's not going to affect us. But just be prepared that when you go to your physics class or your engineering class or your calculus class, this issue is going to come up. A bicycle is moving, so different points on that wheel of the bicycle are going to have different velocities, and situation becomes a bit complicated. So let me go here, make this thing. You guys are going to see that in various courses later on. Instead of a bicycle, I have this circle underneath. Imagine you take a bicycle, turns it upside down, like trapeze artists sometimes do that on a circus, so they're upside down. But in this case, I have this circle. This x-axis is the road, and this is the wheel of that bicycle turned upside down. Notice what happens as I turn around. If you fix your eye on a point on the bicycle, like if you put a colored dot on the rim of the tire of bicycle and follow it as it goes around in a very interesting curve. There's a history behind this curve in mathematics. People study it quite a bit. It has some wonderful properties. For example, if you want to design a slide, this curve comes in there as, in some sense, the most fun slide, meaning it's a slide that takes you from a point to another point in the fastest time. So slides are never flat and straight, rather they are kind of curved, and this is an ideal curve for sliding down in the shortest amount of time. Anyway, we are going to see that in calculus and other courses later on, but right now I just wanted to mention that there is something to look at on given the fact that the bicycle turns. But it is still true. So if you have a bicycle and here's a road and the bicycle wheel is not skidding, so you're not like on ice or something like that, the speed at which the bicycle travels is equal to the radius of your wheel times how fast that the wheel turns. So this is still true that the velocity of the bicycle is the radius of your wheel times the angular speed of the wheel, meaning how fast you are pedaling essentially, or how fast that wheel is turning. Of course, there you have gears, and that changes the speed, how fast you pedal versus how fast the the wheel actually itself turns. So this is for the wheel. So what do we have here? We are given that the bicycle, so it's a big bicycle, is 30 inches for the radius of the wheel. It is turning at the rate of 300 revolutions per minute. So the revolution rate that we have is 300 per minute. Always remember, first you want to convert your revolutions to radians. So if we set revolution to radians, one revolution is 2 pi radians. You go do that. So we say omega is 2 pi 300. So this, now we call it radians per minute. Okay. Well, what is the velocity is going to be? You just take 30 inches. So this is 30 inches times 2 pi times 300. So what would be our unit now? Well, let me write this thing again. So I have 30 times 2 pi times 300. Since the radius is given in feet, we are going to have feet now. Since the radius given in inches is given in inches, velocity that we get is in terms of inches per minute. So what is it that we want? Well, we want something quite different. We want in terms of miles per hour. So we have some ways to work to get there. So we say inches. First, we are given some little bit of hint that 1 mile is 5,280 feet. So I convert this thing to feet first. So I multiply by I have to divide it by 12 to get the foot, and then I have to say that 5,280 feet is equal to 1 mile. So what we have now is a product of 30 times 2 pi times 300 times 1 over 12 times 1 over 5,280, and now we have our answer in terms of inches, miles. We are still per minute. We still have to do one more conversion. How do I convert from minute to hours? I say, well, 60 minutes is equal to 1 hour. So the minutes now cancel. The velocity that I get is going to be equal to this number. Okay, for the next problem, we have something from planetary system. It says Saturn has a radius of 37,000 miles. As the planet rotates on its axis, a point on its equator travels at about 500,000 miles per day. It's a big planet, so by the way, that day means our day, not Saturn's day. At any rate, find the angular speed of a point on its equator in radians per day, and find the number of rotations that the planet makes per day. So this is no different from all the other problems we have been doing so far. So let's just draw a picture, make sure all these strange numbers wouldn't detract us. So we have this planet, so planet Saturn it has a radius of 37,000 miles. So this is 37,450 miles. So this is R. And if we consider a point on equator and check to see how fast it is traveling, the velocity that we get or speed that we get is 527,800 no 787 miles per day. Okay, so the numbers are unusually large, just astronomical type of numbers. And what we want to do is to find the angular speed of a point. So as this point turns around, what is the omega of it? No different from everything that we have done so far. So the speed or the velocity is as before, r times omega. So we have 527,787, that is miles per day. That has to be equal to R, which is 37,450, that's also miles, and then times omega. So what would be the dimensions of omega in this case? So miles and miles cancel, and what we get is radian per day. So radians per day. And thankfully that is what we are asking for here. So our omega is simply a ratio of this large number to that large number, 527,787 divided by 37,450, and our unit is going to come in terms of radians per day, which is exactly what this one wants, so we don't have an issue of conversion. So we divide these two, and we get almost something like, let's see, we divide it 527,787 and divide that by 37,450, and I get 14.09, and it says to the nearest whole number, well, to the nearest whole number it's just 14 radians per day. Next, it's asking us number of rotation the planets makes per day. Again, remember, this is our day. Of course, with respect to its own day, it just makes one rotation per day. That's not what the question is. Not that. The question is, in 24 hours of Earth day, how many times does this planet Saturn turns around its own axis? So what we do, we said omega, or one revolution, was equal to 2 pi radians. So if you have the radians, you divide it by 2 pi, you see how many full rotations fit in it. So I have 14.09. So really I have to take this fraction, and divide it by 2 pi, because it says don't make intermediate computations so that we don't lose any accuracy. But let me just do it like this, and then we come back. So when you divide it by 2 pi, so you have to divide, of course it's 14.09, you carry a few more digits, this is 3.14, etc. Carry a few digits here, and you divide it, and out comes 2.24, and to the nearest whole number is going to be 2 rotations or 2 revolutions per day. So it kind of turns around its own axis twice as fast as ours does. Okay, so I hope you came along, even though the numbers are strange. Sometimes you can simplify numbers in your mind so that you can carry out the computation without getting distracted. Like if you these big numbers kind of bother you, you can kind of change it, like this one, change it to 50, this one change it to 3, kind of proportional changes, and then solve that problem, come back and do it with the actual original numbers to make sure that you're not missing anything. Okay, one last problem here. Sorry, this one is saying angular and linear speed. Again, a ceiling fan has a 16-inch blade. So we have a fan, so hopefully looking better than this fan that I'm drawing. So it has a 16-inch blades. The linear speed at the tip of the blade is 6 feet per second. So if I take this point and see how fast it is moving, that turns out to be 6 feet per second. Okay, what now? We are looking for angular speed. It's always in radians. Now we have an additional task also. It says per minute. Okay, the original says per second, and now the answer is, well, per minute. How fast is it going to go? Of course, every minute is 60 seconds. We need to know that. So as before, we say well, we know the velocity. Velocity is 6 feet per second. We know that v is equal to r omega. We know r is 16 inches. We already see that this is feet, this is inches. We gotta use same type of units throughout so that the cancellation works out properly. So either we have to change the inches to feet or change the feet to seconds, either way. So I can say this is 16 inches. How do we modify the units? You multiply by a fraction, opposite location as a unit that you have to have same units, and then in the other place you want to have your new unit. So if you want in terms of feet, you have to cancel the inch by another inch here. So now I compare feet and inches. I say 1 foot is equal to 12 inches. Once I have that, then I can cancel these inches, and of course I have 16 over 12. Of course you could have said that without going through all these steps, but just to practice how to change our units. 16 inches we have to divide by 12 to figure out how many feet that is. You can leave the fraction like that, or simplify and like divide by 4, get 4/3 of a feet of a foot. That's the radius. So now I write this is 6 feet per second. R is 4/3 of a foot times omega. Omega, what would be the unit of omega? The time unit would be borrowed from your velocity. So the time unit here is going to be per second, and it's going to be always radians per second. So what is omega going to turn out to be? 6 times 3 divided by 4. So we are really taking 6 and dividing it by 4/3. However you want to do that, so it becomes 18/4 or 9/2. And what's the unit? It's radians per second. So we had an additional complication here, which is we want it per minute. So how do we change that? This is 9/2. This is radian per second. So I don't want second. So I put a second up here to cancel the second. What is it that I want? I want minutes because it told me minutes. Okay, so that the seconds cancel. Well, what's the comparison of second and minute? 1 minute is 60 seconds. Okay, so you need the conversion here so that this fraction has to be equal to 1. 1 minute is equal to 60 seconds, meaning physically speaking these two have to be the same thing. So 60 divided by 2 is 3 times 9 becomes 270. This is going to turn out to be radians per minute. So angular speed, this turned out to be 270 radians per minute. Well, number of revolutions, we had that many times. Revolutions is equal to omega divided by 2 pi. So that's going to be 270 divided by 2 pi. And so you just divide 270 divided by 2 pi. Let me try again on the 270 divided by 2 divided by pi. So this becomes 42.97, etc. Nearest number is going to be 43 watt revolutions per minute. So this becomes 43 rounded to the nearest whole number. Okay, so this wasn't a mini lecture. We went through quite a bit of examples. I know this is from experience that you're going to have a bit of hard time. Several issues. Let's go back to see what happened. So two basic ideas. One is that 1 revolution is 2 pi radians. So we have to be comfortable with the concept of radians. 1 revolution is 2 pi radians. What was radians? If you want to have it's like a yardstick for angles. Take your radius, lay it on the side of the circle. So this is the same length as the radius. When you make this angle is 1 radian. That's our yardstick for angles. 1 whole circle, 1 whole revolution is 2 pi radians. We looked at all these ways of talking about the revolution: a rotation, a round, cycle, spin, turn, lap, orbit, and perhaps a few other things. Item number 2 that we learned is that the linear speed v is equal to the radius times angular speed omega. So we practice this thing in a large number of cases. Again, let me let you know this is an important issue. It's going to come up multiple ways. It's going to come up in your physics or your engineering classes. It's going to come up in your calculus classes. It's going to come up in perhaps even differential equation classes. So it's going to show up. So let me go through all the demos I had for you, just to so that okay, let's start from the easy one. So okay, easy one. A fan sitting in its own location and just turning. This is an old style fan. So the last exercise we did was related to the one of these things. It doesn't even oscillate, it's just sitting there. Okay, next up you're going to see this picture in a variety of textbooks. So is a car that is traveling. It's going at some speed v. The tires have say certain radius r, and the tire is turning at a certain rate omega. So omega is the angular speed, and v is equal to r omega. Okay, here we have v equal to r omega, but we said that the issue of a circle turning on flat surface is going to be source of lots of interesting problems coming up. If you're interested, you have a curve called Brachistochrone. This is an example of it turned upside down compared to that circle that we saw. If you take a circle and roll it on a surface and color certain point of it, like this point, suppose you color that point of a circle, as you let the circle turn, that point is going to travel on a certain curve. There's quite a bit of history with respect to this curve. Let me show you some aspect of it. So there's an entire Wikipedia page for this. You see what's happening. Three balls or something are going to slide on three surfaces, and the red one is our curve. You notice that the ball that's on the or the bead that is on the red curve makes its trip faster than other two. So the best slide isn't a straight slide, rather it goes on this particular curve. So that's the mathematical origin of this problem, but it keeps showing up all sorts of places. Let's move on to the next example that we had. So this is for planetary movements. So this demo is showing Mercury going around Sun. You know that Mercury is the planet that is closest to the Sun and has a very oval looking orbit, and that causes quite a bit of interesting things. This arrow that you see here, that is showing that Mercury is turning around its own axis at the same time that's turning around the Sun. However, the combination of these two motion makes it quite a complicated and interesting phenomena. So here is how things might look on a day on Mercury. So that is the Sun is coming out. So suppose you are on Mercury and sitting there and looking at the sky. Sun comes up there, hovers up there for a second, goes back for a while, and then you have a sunset. Let's look at it again and see a very peculiar sky for Mercury. Okay, it comes up at noontime, kind of hangs around there, goes back a little bit, and then moves forward. They call that retrograde motion. Well, traveling to Mercury to see this is going to be beyond our capabilities these days, but there is something that people could see from thousands of years ago: retrograde motion of planets. So here we have Sun, this is Earth, and this is Mars. So we have two circular motions, and each of them have their own angular velocity. And when you have multiple angular velocities, all sorts of interesting things happen. So what happens here? Let's go look. This is a interesting page, Astrogirl West, if you want to go look at it. So let's see. Here Earth and Mars are moving. So from when we are looking at the Mars from Earth, when we were up here against the background of the sky, we would have seen Mars to be up here. A few days later, we see Mars coming down here. A few days later, we see Mars coming coming down here, and then Mars will appear in the sky to be backing up. They called that from ancient times the retrograde motion. So that created a lot of headache for ancient astronomers to explain how does this thing go backward, and then it starts to have a regular motion after that. So if you're interested in astronomy, this is something that you want to look at. Very interesting phenomena called retrograde motion. You can see it how people in ancient times, like 2500 years ago, tried to justify this, what concepts they come up with, and then around the time of Copernicus and others, they had alternative ideas as to how things move. So if you assume the Earth is at the center of the universe, you will have a hard time explaining this retrograde motion, but when you change your perspective, things turn out to be rather easy to explain. Okay, so we went on a tangent there to explain this angular and linear speed is a very important topic. Once again, all that is needed for your problems is that v is equal to r omega, and that one revolution is equal to 2 pi radians. Linear speed is equal to radius times angular speed, and each rotation is 2 pi radians. Other than that, the thing that we had to watch out for was changing units. Okay, you want to practice changing units, because definitely it's going to come up in your future classes. If you have questions, do bring it up, and we can solve more examples in a one-to-one discussion in office hours. Okay, until next time, good luck and God bless.